Welcome to this comprehensive guide on C# fundamentals, specifically tailored for beginner programmers. We'll explore essential concepts that form the bedrock of robust and efficient C# applications, providing you with a solid understanding to build upon. Today, we'll demystify three core concepts crucial for any C# developer: constructors, garbage collection, and the iDisposable interface. Understanding these will significantly enhance your ability to write clean, performant, and resource efficient code. Let's begin our journey by understanding constructors, which are essentially the blueprints for creating objects in C#. They play a vital role in ensuring that every object is properly set up and ready for use the moment it's instantiated. Constructors are special methods automatically called when a new object is created from a class, ensuring it's properly initialized with a valid state. This automatic invocation guarantees that an object is never left in an undefined or unusable condition. They share the exact same name as their class and are crucial for setting up an object's initial state, making it immediately functional. This naming convention clearly links the constructor to the class it belongs to, defining its creation process. The default constructor has no parameters and is automatically provided by the C# compiler if you don't define any explicit constructors yourself. It serves as a basic, parameterless way to instantiate an object when no custom initialization is specified. This implicit default constructor initializes numeric fields to 0, booleans to false, and reference types like strings or other objects to null. It ensures a predictable starting point for all data members within a newly created object. Parameterized constructors accept arguments, allowing you to pass specific values to initialize an object's properties right at the moment of creation. This provides flexibility, enabling you to create objects with diverse and custom initial configurations. Constructor overloading means a single class can have multiple constructors, each with different parameter lists, enabling diverse initial states for objects. This flexibility allows you to instantiate objects in various ways, depending on the available input data. A copy constructor creates a new object by duplicating the values from an existing object of the same class. This is particularly useful when you need an independent, identical replica of an object without modifying the original instance. Private constructors restrict object creation from outside the class, often used in design patterns like singleton to ensure only one instance of a class exists throughout the application's lifetime. This enforces strict control over object instantiation. Static constructors initialize static members of a type and are called only once, specifically when the class is first accessed or any static member is referenced. They are parameterless and ensure static data is set up before any other operations. If you don't define any constructors within your class, C# implicitly creates a public, parameterless default constructor for you. This ensures that even without explicit definition, objects can still be instantiated with default values. However, you can explicitly define your own constructors to implement custom initialization logic, overriding the default behavior. This gives you precise control over how an object state is established upon its creation. The order of execution during object initialization is precise and well-defined, starting with instance fields being set to their default values, followed by the execution of any field initializers you've defined in your class. Base type field initializers and constructors run before the derived class's instance constructor, ensuring the base class is fully initialized first. This hierarchical process is then followed by any object initializer specified during instantiation. Next, we delve into garbage collection, C#'s automatic memory management system, a fundamental feature of the .NET runtime. This system is designed to simplify memory handling for developers, preventing common memory-related errors. Garbage collection, or GC, automatically reclaims memory from objects that are no longer referenced or needed by your application. This process frees up valuable system resources, allowing your program to run more efficiently without manual memory deallocation. The Common Language Runtime, or CLR, actively manages this entire process, ensuring efficient use of system memory without constant developer intervention. The CLR's sophisticated algorithms optimize when and how memory is reclaimed. The GC identifies and used objects by tracking references and then frees their memory, effectively preventing common issues like memory leaks and dangling pointers. This automatic cleanup significantly reduces the burden on developers. To optimize performance and reduce the frequency of full collections, .NET organizes objects into generations based on their age. This generational approach allows the GC to focus its efforts on areas where memory is most likely to be reclaimed. Generation 0 is where new, short-lived objects are initially allocated. It is the smallest and most frequently collected generation because most objects become unreferenced very quickly after creation, making its collection highly efficient. Objects that survive a Generation 0 collection are then promoted to Generation 1, indicating they have a slightly longer lifespan. This promotion helps the GC differentiate between short-lived and potentially longer-lived objects. Generation 2 contains long-lived objects that persist for extended durations throughout the application's execution. These objects are collected less frequently, as they are expected to remain in use for a significant period. The GC process involves several phases, starting with marking, where the collector identifies all live, reachable objects. Any objects not marked as live are then designated as unreferenced and marked for subsequent cleanup. Next, the relocating phase updates the memory addresses of live objects, preparing them for compaction. This step ensures that all references correctly point to the new locations of objects after memory is reorganized. Compacting then frees memory from dead objects and eliminates any gaps created by their removal, reducing fragmentation and speeding up new memory allocations. This process creates contiguous blocks of free memory, improving allocation efficiency. Garbage collection is typically triggered automatically when the allocated memory exceeds a predefined threshold or during low memory conditions detected by the system. These automatic triggers ensure timely memory reclamation without manual intervention. While developers can explicitly trigger GC using GC collect, it's generally discouraged as the GC is highly optimized to run automatically and efficiently. Manual invocation can often lead to suboptimal performance and should be avoided unless absolutely necessary. Finalizers, denoted by class name, are special methods called by the GC just before an object's memory is reclaimed. Their primary purpose is to clean up unmanaged resources that the object might be holding, such as file handles or network connections. Finally, let's explore the iDisposable interface, which is absolutely essential for managing unmanaged resources in C#. This interface provides a standardized way to ensure that external resources are properly released. iDisposable provides a crucial mechanism for releasing unmanaged resources, which include things like file handles, database connections, network sockets, and graphics device contexts. These resources are not automatically managed by the garbage collector. Managed resources, such as objects created within the .NET framework, are automatically handled by the garbage collector. However, unmanaged resources, which are external to the .NET runtime, require explicit developer intervention for proper cleanup. The iDisposable interface contains a single, critically important method, dispose. You implement this method to define the specific logic for releasing any unmanaged resources that your class might be holding, ensuring their timely cleanup. The using statement simplifies this resource management process significantly, ensuring that the dispose method is called automatically and reliably when an object goes out of scope. This guarantees proper cleanup even if exceptions occur. The standard dispose pattern involves a public, parameterless dispose method that calls a protected virtual dispose. This two-part structure allows for flexible and robust resource cleanup, handling both managed and unmanaged resources. Within the protected dispose method, if disposing is true, both managed and unmanaged resources are released. If disposing is false, meaning it's called from a finalizer, only unmanaged resources are released, as managed ones are already gone. A Boolean flag, typically named disposed value, is used within the dispose pattern to prevent multiple calls to dispose. This ensures that cleanup operations happen only once, avoiding potential errors or redundant resource releases. Always use the using statement for any objects that implement iDisposable to guarantee proper and timely resource cleanup. This is the most reliable and recommended practice for working with disposable resources in C#. You should implement dispose in any class that directly uses or wraps unmanaged resources, or if your class owns other objects that implement iDisposable. This ensures that all resources are accounted for and released. If your class owns other disposable objects, it's crucial to ensure they are also disposed of correctly within your own dispose method. This creates a chain of disposal, ensuring all nested resources are released. Call gc.suppress_finalize inside your public dispose method to avoid unnecessary finalization overhead. Once dispose has explicitly cleaned up resources, the finalizer is no longer needed, improving performance. iDisposable ensures the prompt and efficient release of unmanaged resources, preventing resource leaks that can degrade application performance and stability. It provides deterministic control over resource lifetimes, which is vital for system-level interactions. To prevent memory leaks, it's crucial to unsubscribe from events when objects are no longer needed and to use weak references when appropriate to avoid strong references that can keep objects alive unnecessarily, hindering garbage collection. Memory profiling tools are invaluable for identifying subtle memory leaks and analyzing complex memory usage patterns within your application. These tools provide deep insights into object allocations and lifetimes, helping you optimize resource consumption. Understand the fundamental differences between value types, which are stored directly on the stack or inline, and reference types, which are allocated on the heap, to optimize memory usage effectively. This knowledge guides efficient data structure design. Object pooling and reusing objects instead of constantly creating and destroying them can significantly reduce memory allocation overhead and the frequency of garbage collections. This strategy is particularly effective for frequently used, expensive to create objects. Minimize the use of very large objects to avoid fragmentation in the large object heap, or LOH. The LOH is not compacted as frequently as other generations, so large objects can lead to memory inefficiencies if not managed carefully. Remember, forcing garbage collection using GC Collect is generally discouraged because the CLR's automatic process is highly optimized. Trust the runtime to manage memory efficiently. Manual intervention often does more harm than good. For frequent string concatenation operations, always use String Builder instead of repeatedly concatenating string objects. String Builder prevents the creation of numerous intermediate string objects, significantly reducing unnecessary memory allocations and improving performance. Mastering constructors, garbage collection, and the iDisposable interface is absolutely crucial for writing robust, efficient, and high-performing C# applications. These concepts are foundational for effective resource and memory management. Keep practicing these concepts, applying them in your projects, and you'll build a strong, professional foundation in C# programming. Continuous learning and application are key to becoming a proficient and skilled C# developer.